I wish to thank the organizers for the invitation to give a keynote here. It's a great honor. What you see behind me is a cartoon that I made for my little website on AI against the coronavirus just a few days ago. And much of what I'm going to tell you will be reflected in this website. Artificial intelligence based on deep neural networks and deep learning can help to fight the COVID-19 virus in many ways. The basic principle is very simple. Neural networks can learn to detect patterns in data from viruses, patients, others, and we can use those neural networks then to predict future consequences of possible actions, and we will act to minimize damage. And I'll mention a few examples. One can track populations through pattern recognition. Many of you probably know the Bluetooth peer-to-peer apps on your smartphone, which allow you to prevent dangerous contacts to a certain extent. Not so much AI is needed for that. It is more challenging to recognize faces or gaits of people and their contacts in videos taken by drones or in the street. That's harder, but it's possible. And the ways of doing that actually go back a long time. In 2011, almost a decade ago, my brilliant postdoc, Jrgen, was the first to create a deep and fast neural network which was able to win pattern recognition competitions. And back then, a decade ago, for the first time, superhuman performance in computer vision was achieved in a contest in Silicon Valley. And much of modern computer vision is extending this approach. And especially in China, it's widely used today. Neural networks can also learn to predict outbreaks, to build early warning systems. And there is a Kaggle COVID-19 forecasting challenge on that. And neural networks can also learn to predict future demand for limited resources, such as ventilators and doctors, to optimize logistics. And you can call that predictive maintenance of the population, if you will. One can also sequence virus genomes, that's what's being done all the time, and predict where similar genomes are going to appear next. Because maybe you know that the virus genome is mutating all the time randomly, and that's how you can trace it back in time where it's coming from. And that data can be fed into AI systems that then learn to predict the future evolution, future expected evolution of these observations. Neural networks can also learn to monitor single patients. For example, they can monitor your heart rate, and they can track your biosignals, your breathing, your coughs, and other signals. And my little website that I mentioned before has a bunch of references on recent applications of this to the coronavirus crisis. And neural networks can also analyze images, such as X-ray images of lungs or chests of patients, and they can diagnose pathologies. And again, my website has a bunch of references on that. By the way, the first medical imaging contest won by deep neural networks dates back to 2012. And again, it was my postdoc, Jrgen, and his colleagues in my little team. And this was on cancer detection. What you see behind me is a picture of the slice through a female breast. And some of these cells that you see there are harmless and others are dangerous. And normally it takes a trained histologist to, but in this contest, we were able to teach a neural network to imitate the histologist, and that's how the system suddenly was able to outperform all these competitors. And today everybody is doing this, not only startups, but also the big companies such as Siemens and Google and IBM. This actually was part of our recent decade of deep learning. Between 2010 and 2020, computers suddenly were fast enough to allow commercial applications of all these techniques that we have developed a long time ago. And much of that actually goes back to the early 90s. And I'm always claiming that we had this miraculous year in the year 1990 to 1991, when many of the basic concepts that have become very popular later were published for the first time, but computers were 1,000,000 times slower than today, and nobody could do much with that. And this has greatly changed. Neural networks can also partially automate drug design, and I find this very exciting. For example, neural networks can help to find molecules that dock on the folded proteins of this virus. The virus is simple. It has just a few proteins, and the goal must be to inhibit the activity of these proteins, much like antibodies do, such that you can block the entire self-replication machinery of the virus. And already in 2007, when compute was almost 1,000 times more expensive than today, the deep neural network called long short-term memory, or LSTM, excelled at predicting protein folding. And this was done by my former student, but now professor in Linz, Sepp Hochreiter, in 2007. And to predict folding like that is important for finding docking stations. Google DeepMind recently also had computational predictions of protein structures associated with the virus. By the way, the first DeepMinders with publications in AI and PhDs in computer science actually came from my little lab here in Switzerland. One of them was co-founder of the company, and the other one the first employee. So what's this LSTM, which I just mentioned, which has been so successful in predicting the folding of proteins in 2007? It's much older than 2007. It goes back also to the early 90s, and it's a neural network, a recurrent neural network, a little bit inspired by the human brain. In the human brain, you've got maybe 100 billion little processors called neurons, and each of them is connected to maybe 10,000 other neurons. And some of these neurons are input neurons where data is coming through the cameras and the microphones. And some of these neurons are output neurons, and if they are switched on, then your finger muscles move or your speech muscles move. And your life is basically about translating these incoming inputs into action sequences that lead to success. Now, all these connections have a little strength, and it's called the weight. And in the beginning, all of these weights are random, which means that the influence that one neuron onto another has is random too. But then, through learning, some of these connections get stronger and some of them get weaker, such that in the end, the network can learn to do something interesting just by following training examples. For example, it can drive a car or do speech recognition and stuff like that, or predict coronavirus folding, all kinds of things like that. And I don't have the time to go into the details of that. However, at least I can mention in the slide behind me the names of the brilliant students in my lab that have made that possible. First of all, Sepp Hochreiter, my first student ever, already in 1991, he had fundamental insights in his diploma thesis. And then Felix Geers, in my Swiss lab already, not any longer at Tech University Munich. And then Alex Graves, a Scottish guy who also had great contributions, Dan Wiestra, Justin Bayer, and a couple of other important students who made LSTM what it is today. And what is this used for today? You don't know it so much from protein folding prediction. No, you know it from your smartphone because you have an LSTM on your smartphone where it is doing much of the AI applications there. For example, speech recognition. Since 2015, whenever you interact with a search engine through the voice channel, when you say, okay, Google, what is the shortest way to the station? Then it understands what you say and it translates that into a query for the search engine. And it's much better than what they had before. And today that's on billions of smartphones. And also, shortly after that, LSTM started to become really useful for translating from one language into another. And this is now also on many, many smartphones. By 2017, Facebook Translate already did about 30 billion translations of messages through LSTM per week. 30 billion. If you compare that to the most successful YouTube video that has about 6 billion clicks, but it needed 2 years for that. So LSTM is useful for many kinds of sequence processing. Protein folding is just one of these possible applications. However, back then, 1991, when we started with this whole deep learning thing for recurrent networks, we could do only little toy experiments because computers were really 1,000,000 times slower than they are today. Fortunately, however, every 5 years, computing became 10 times cheaper. And that's an old trend. It was even old in 1990 because it started at least way back in 1941 when this man, Konrad Zuse, built the first working program control general computer. That was between 1935 and 1941. And he could do roughly 1 operation per second. 1 operation per second, like a single multiplication per second. But then 30 years later, you could do roughly 1,000,000 operations like that for the same price. And so on. And today we can do roughly 1,000,000 billion operations per second for the same price. And suddenly computers and smartphones and everything are powerful enough to really exploit the power of these old algorithms from the previous millennium. By 2009, computers were fast enough such for the first time LSTM was able to win pattern recognition competitions through the efforts of my previously mentioned PhD student Alex Graves. And then came our decade of deep learning where suddenly everybody started to use that, which makes me happy. It's really great to see that decades of research have eventually led to something that really influences billions of people all over the world and currently really can play a role in fighting the coronavirus. One can also teach chemistry to LSTM or to feed-forward neural networks or to graph neural networks, which were pioneered in 1995 by Goller and Küchler, the graph neural networks. How does that work? You have input substances and certain conditions such as temperature and catalyzers, and then a chemical reaction takes place and it produces output substances. And if you have a database with millions of examples like that, the network can learn to map these input ingredients to the corresponding output substances. And in the process, it learns about chemistry. And you can use it as a stand-in for what physics and chemistry really do, which means you can, once you have trained it on lots of examples, once you have made it an artificial chemist, you can use it to come up with new compositions of ingredients to achieve new output substances that you never have seen in this way. For example, you have certain desired properties of the output substances, and then you can work the neural network backwards and figure out which kind of input substances do I need, given this model of chemistry, to achieve these desired results. And the jaws of chemical engineers dropped when they saw how well this can work. In recent years, this really has started to revolutionize chemistry. And neural networks are now sometimes even good enough to replace wet lab tests, the so-called assays. Neural networks won already 8 years ago the Merck Molecular Activity Challenge. That was done by the University of Toronto. And they also won the Tox21 Data Challenge on predicting the toxicity of substances. That was done by the University of Linz in Hochreiter's group. Neural networks can design new molecules. For example, Segler and colleagues had a famous paper about that in 2018. And they also can find the antibody needle in an antibody repertoire haystack. That was again done by the University of Linz, which has a very strong bioinformatics group, which is using deep learning in many ways to improve the situation in chemistry, in drug design, and so on. For example, the ligand-based approach goes like this. Given a certain molecule, a neural network learns to predict to which proteins it will bind. Again, done by the University of Linz. And my little website, AI versus COVID-19, has references on that. The typical drug discovery development pipeline takes too long. It takes at least 6 years for selecting maybe 5 out of 10,000 compounds, and it takes 7 years of clinical trials afterwards, where you then study just a few things that are very promising, and then it still takes 1 year or more of approval. And that's too long, especially at the times of the current pandemic. But one can speed this up by fast virtual screening. Use a large database, such as the Zinc database, which contains descriptions of maybe 1 billion molecules. And then pipe the data through a deep neural network called the SMILES LSTM. The SMILES LSTM, which also goes back to the University of Linz. And it suggested about 30,000 top-scoring molecules as inhibitors of SARS-CoV-2, of this virus. And then once you have this greatly reduced set of candidates, you start testing in the wet lab. And you can also apply this approach to drugs which are already on the market, which is important because that's the way to reduce these costly clinical trials. Just a few days ago, there was the JEDI challenge on that. On the 9th of April 2020, this grand challenge started, which is called 1 billion molecules against COVID-19. And there's 2 million euros prize money on this. JEDI calls itself the European Moonshot Factory, and that's one of the first moonshots that they have there. Again, my little website, AI versus COVID, has links to many additional resources to help with COVID-19 research. Most of what I have been talking about so far is about supervised learning. However, we also have methods that don't slavishly imitate human teachers, but that create their own goals and that curiously explore the world like little babies do, like little scientists do. Little babies are little scientists, and they don't learn much from their parents. A little bit they learn from the parents, but much of what they learn is learned by inventing experiments with the toys. How do I change the inputs that are coming in through my actions in the real world? And that's how little babies learn, by playing, to understand gravity and other aspects of physics and so on. And since 1990, we've been working on little artificial agents that really create their own experiments, self-invented experiments, to create situations in the world from which they can learn something that they didn't know yet. So the curious little babies are the same principles that we find in scientists 20 years later, and the only difference is that the experiments are becoming. And we have artificial scientists that are getting smarter and smarter in this way, and it may be too late for the coronavirus, which needs a very fast response, but the future is going to be about artificial scientists that creatively and curiously learn about the world by inventing their own goals and their own experiments. And in principle, we already know how to do that. Many people want to know, how does COVID-19 affect the economy? And I should know, because I have a startup called Nascence, which is affected because our clients are affected. All the major companies in the world, all the famous manufacturers of all kinds of devices are affected. However, as all the Chinese know well, a crisis is also an opportunity. And actually, the industry is going to emerge stronger from this crisis than it was before, because the machines that they are using are going to become smarter, and they will be able to do all kinds of things that they couldn't do before, using artificial brains like the ones that we are constructing at Nascence. Nascence is pronounced like birth in English, like nascence, but it's spelled in a different way. NN for neural networks, AI for artificial intelligence, and it's about the birth of a general purpose neural network-based artificial intelligence. Here are some pictures taken with the guys that are collaborating with us in several exciting projects: Audi, Festo, and its robot hands, EOS, which is a leader in 3D manufacturing and 3D industrial printing, Schott, which is a leader in making glass, and maybe you have their glass in the lenses of your smartphones because they are owned by the Zeiss Foundation. And Sulzer Schmid, which is using drones to inspect wind turbines without endangering any. Let me finally emphasize that AI is for all. AI is not going to be dominated by just a few big companies. No, it's getting cheaper all the time. Every 5 years, it's getting 10 times cheaper, as I mentioned before, which means within 30 years, it's going to be 1,000,000 times cheaper. It's going to make human lives longer and healthier and happier, and it has already started doing that. I remember 40 years ago, I had a rich friend. He owned a Porsche. But the most amazing thing was that in the Porsche, he had a mobile phone, which means he could talk to other guys who also had a Porsche like that while being on the road. It was the most incredible thing. Today, a few decades later, billions of people, also in developing countries, have smartphones that are much better than what he had back then. And the same is going to be true for AI. Everybody is going to have cheap AIs, making his life better in many different ways. So in the end, all will be good. I started this talk with a cartoon of a robot And I will end it with the cartoon of a robot, which I drew a long time ago, 33 years ago, 1/3 of a century ago, behind me. It's the cover of my diploma thesis from 1987. My diploma thesis was very ambitious. It was about building a machine that not only learns, but also learns to improve the way it learns, and learns to improve the way it learns, to improve the way it learns, and so on recursively. Metalearning, this is called. And back then, few people were interested, but today it's a hot topic. And in many ways, it has defined my life since then. But that's not my final slide. My final slide is about something related to COVID, namely the coronavirus geopolitics. 100 years ago, the Spanish flu emerged, not from Spain, but apparently from North America, apparently from Kansas. A few months ago, COVID-19 emerged, apparently from China. Long before that, many centuries ago, germs and viruses and diseases went hand in hand with the fall and the rise of empires. And if you want to read a few thoughts on that, you have a look at this little webpage that I made just for you. Thank you very much for your patience.
Jürgen Schmidhuber, sir. I would like to invite Professor Pushpak Bhattacharya, who is a professor at Computer Science and Engineering Department at IIT Bombay. His research areas are natural language processing, machine learning, and AI, and has published more than 350 research papers in various areas of NLP, including the textbook Machine Learning. He is also a fellow of Indian National Academy of Engineering, Abdul Kalam National Fellow, and former president of ACL, highest international body for disseminating ML and NLP research. We can start the interview session.
Okay, thank you very much for this kind introduction. And we are indeed absolutely privileged to have Professor Jürgen Schmidhuber amidst us, ornamenting the Techfest of the Institute. I understand there is a video to be played initially. Is that so, Ashay? After which I'll introduce Professor Jürgen.
So we have done that. We may begin with the session.
Oh, we may begin with the session. Okay. So let me first introduce Professor Schmidhuber, which is, as I said, a privilege for me. The media have often called Professor Jürgen Schmidhuber the father of modern artificial intelligence and father of deep neural network. Since the age of 15, Professor Schmidhuber's main goal has been to build a self-improving AI smarter than himself. His PhD thesis back in 1991 laid the foundation of the famed long and short-term memory, LSTM. The 1997 paper on LSTM in neural computation has gathered over 40,000 citations till date. In 2011, his group achieved a dramatic speed up of 60 times over the state of the art in convolutional neural network. Professor Schmidhuber's lab's research and development on DNN have revolutionized machine learning and have been used in over 3 billion smartphones for Facebook's automatic translation Google Speech Recognition, Google Translate, Apple Siri, and QuickType, Amazon's Alexa, and so on. It is indeed miraculous to have example of such work, such impactful work in this world. He also pioneered unsupervised adversarial networks, artificial curiosity, and meta-learning machines that learn to learn. He is recipient of numerous awards and chief scientist of the company enlightens, which aims at building the first practical general purpose AI. So we are indeed very fortunate to have you, Professor Schmidhuber. Maybe we can begin with the questions that the students have prepared for you, and we would like to have your views on many of the fundamental issues of AI. The first question is, you have always spoken about AI that can become smarter than human beings themselves and have contributed greatly towards this research. When did this idea first originate in you? And what inspired the gestation of this idea?
Dear Pushpak, thank you very much for the introduction and for the first question of the students. Well, the idea really dates back to my teenager times. And back then, when I was a teenager, I had a science hero that was Einstein. And I thought, I want to become a physicist like Einstein, such that I can work on the most fundamental problem, on the nature of the universe, trying to better understand the world and everything that is in it through understanding the basic physical laws. And then I realized that I'm not very smart.
Oh.
And then I realized maybe I have a chance of building something that learns to become much smarter than I could ever hope to be. And that could learn to become a much better physicist than I could ever hope to be. And that this smarter scientist is going to solve all the problems that I cannot solve myself. And I thought back then when I was a teenager, that was in the 70s, that it may be possible to build something like that, such an AI which learns to improve itself, to build something like that within my lifetime. And that's how it all started. And I still think that this big overarching goal of my life can be achieved before I die. Of course, I can be hit by a meteor tomorrow. I can have a heart attack and it will be over. But if I'm lucky, I'm going to live a few more decades and I will see how it happens. And then all of what we know is going to change.
Wow. So that was a great answer. And we of course pray that God gives you a very long and fruitful life. Now, a question that arises in our mind naturally is questions related to LSTM. And how did vanishing gradient attract you? When did you encounter vanishing gradient problem?
So in the 1980s, we already, there existed neural networks, even recurrent neural networks, but they couldn't learn much. They couldn't learn to deal with problems where there are long time lags between the relevant events. And only very simple sequences could be learned. And then I tried to overcome this problem. That was in 1991, where I used unsupervised pre-training to overcome this problem. How does that work?
I took a whole hierarchy of neural networks, and the lowest level neural network, recurrent network, just tried in unsupervised fashion to predict the next element in a stream of elements. So for example, suppose we have sentences that we want to classify. Does this sentence contain a certain expression or not, you know? And then it is greatly helpful to take this long sequence of letters and somehow find a way of compressing it down to a much shorter sequence, such that it is easier for supervised learning to learn this stuff. And then I said, okay, let's take the lowest level network. It just learns to predict the next thing. It doesn't even know anything about unsupervised calls. It just learns to predict the next letter given the previous letters. And everything that can be predicted is already known. And only the unpredictable letters, only the errors have to be sent to the next level where there is another recurrent network, which is clocking more slowly. So maybe down there, the first network clocks every single step, but then only every 10th letter is not predictable, and I send up only the unpredictable letters. And then the second level tries to predict these unpredictable letters, again from the previous unpredictable letters, and so on. And then we get a hierarchy where maybe, if we are lucky, more and more predictability is used. And now you see that everything that is predictable can be compressed, because what I can predict, I don't have to store extra. And so from the top level of the hierarchy, I can exactly reconstruct the original sentence, which means that the top level of the hierarchy has a very compact representation of this long sentence. And then suddenly, with this top level representation, I can use supervised learning to learn that. So I call that the neural history compressor. And back then, I had a very smart student. His name was Sepp Hochreiter. And his task for his own diploma thesis was to implement this history compressor and to see how well it works and so on. But then Sepp did much more than that. He also analyzed mathematically what exactly is the problem. Why is it so hard for deep networks to learn in presence of depth and long time lags between relevant events? And he saw and formalized and analyzed in his thesis mathematically that as you are propagating error signals backwards through this backpropagation procedure, which was published in 1970 by the Finnish guy, by the Finnish master student Seppo Linnainmaa, long time ago. 50 years ago, Seppo Linnainmaa had this backpropagation procedure. It is also known as the reverse mode of automatic differentiation. And then Sepp, 20 years later, in 1991 roughly, he discovered what is the problem if you apply this procedure to deep neural networks. And he showed that as you are propagating errors backwards in time or through a deep network with typical activation functions, the errors get smaller and smaller, or they explode both in an exponential way. And in both cases, nothing can be learned. And that's the vanishing gradient problem or the exploding gradient problem. And out of this analysis came the long short-term memory, the LSTM, which is overcoming the problem through a very stupid, simple trick, which is just have a central unit with a constant connection of 1.0 pointing back to the cell, to this constant error carousel, as we call it. And then as you're propagating errors back along these connections, these 1.0 connections, because you have a linear activation function with derivative 1.0, you are propagating always back 1.0 times 1.0 by times 1.0, and you see nothing explodes exponentially, nothing vanishes exponentially. No, you just have a constant multiplication of 1.0 by 1.0 and so on, which means that suddenly you can bridge time lags. The error signals can bridge really long and deep paths, credit assignment paths, such that you can propagate errors back for thousands or millions of time steps. And once you have that, then you still have to surround this linear thing, this linear unit, by a couple of nonlinear gates, such that these gates can take the error signals which are being propagated back in the simple constant linear unit and can use these error signals to learn when to open and when to close, such that parts of the network can influence each other, such that all these things can be learned that currently are being learned by LSTM, from speech recognition to machine translation, and so on. So that is, in a nutshell, the nature of this vanishing gradient problem and its solution.
Thank you so much. It is not only useful for students, it is also useful to teachers, because when we teach LSTM, we do find students getting a bit puzzled as to why the whole thing works, So to give that intuition is important, and that was very insightful. Thank you very much. So I'll move to more of these interesting questions from students. In many of your talks, you have spoken about meta-learning for achieving something like a machine that could solve problems better than humans. Why is it that we do not still have one such thing, and how can this be achieved?
Yes. So we do have meta-learning algorithms that really learn to improve the original learning algorithms. We do have that. I started my thesis in 1987 just on this topic. So that was 1/3 of a century ago, really about learning, better learning algorithms. And then in 1994, we had a paper on that where reinforcement learning was achieved through a self-referential policy which learned to improve itself. And even back then, a quarter century ago, although computational power back then was 100,000 times more expensive than today, even despite of that, we were able to really show how a system like that, a self-referential, self-modifying policy, can over time learn to improve its learning algorithm and accelerate the intake of external reward. So that is the goal, to get more reward per time interval. And since then, we have lots of working meta-learning algorithms, and some of them more sophisticated, and some of them even mathematically optimal, like the Gödel machine. Or if you look at the recent results of my student, Louis Kirsch, who also has done very recent, very interesting work on learning reward functions, such that the reward functions can be used to learn better learning algorithms by coming up with better reward functions for certain problems. So all of that is working in principle. It can be shown that it is working. However, the question seems to be, why are we not yet there that these machines keep on learning and become much smarter than humans? One of the reasons is that at the moment, human meta-learning still has many more resources than artificial meta-learning, because at the moment, human brains are still much more powerful than any cheap computers. As you probably know, a human brain may consist of 100 billion neurons, each of them connected to 10,000 other neurons, and each of these connections can maybe generate something like 100 elementary operations per second. We don't know exactly. But so there seems to be an upper limit for what a human brain can do, which is something like 10 to the 20 instructions. Probably it cannot do as much, because most of my neurons at the moment, as I'm speaking to you, are switched off, because if they were switched on, my head would explode. Too much heat, But nevertheless, the human brain at the moment is much better at computing a lot than even our fastest GPU servers. On the other hand, it's not going to stay like that, because since 1941, every 5 years, compute has become 10 times cheaper. And so very soon, within the next few decades, we should have for the first time, cheap machines, like a laptop or like a smartphone or something like that, that can compute as much as a human brain can do. And if that is true, then it will take maybe 50 additional years, and we will have, for the first time, simple machines that can compute as much as all 10 billion human brains taken together. So a simple computational device that can compute as much as all of mankind taken together, and there will not be only one such device, but millions and billions and trillions of them probably. So in the near future, the meta-learning algorithms that we already have are going to scale much better than what we see today. And I think we will see astonishing things happening through meta-learning in the not so distant future.
Thank you. Thank you for that insight and foresight, I would say, into future.
What's that?
Yeah. So another thing for which you are really very, very famous is this 2011 work on accelerating the training time of CNNs. It is said that you achieved 60 times faster speed compared to the state of the art. So you combine deep scientific insight with tremendous engineering acumen. So can you also take us to those days to tell us what happened? How did you do it?
Yeah, so this acceleration of convolutional neural networks, or CNNs, that was due to my outstanding Romanian postdoc, Jrgen. And he, in 2010, 2011, found a way of making the CNNs really fast on GPU. Now, CNNs are much older than that. They go back to the work of Fukushima in the 1970s, who had the first working convolutional neural network, the first architecture, the CNN architecture. And then there was Alex Weibel, who was the first in 1987 to combine this convolutional architecture with backpropagation. That is something that Fukushima didn't do, and this combination has become really popular. So neural networks with convolutions combined with backpropagation, the method of 1970 of Lina Inmal, the Finnish guy, this is widely used now in computer vision. And this was invented by other people. And what we did, we just made it really fast, such that for the first time we were able to win competitions. And after Dan Jrgen, this is called the DANet. And in 2011, indeed, for the first time, we were able to win a computer vision contest. And the first one was the Chinese handwriting recognition contest. That was, I think, in May 2011. But then in August 2011, that was in Silicon Valley, the traffic sign recognition competition, which you need for self-driving cars. And there, the DANet was 3 times better than a competing network by the second place, which was the team by LeCun, by Dr. LeCun. And then everybody basically started doing that. And now most of the computer vision applications are more or less what happened back then. So the old ideas of the previous millennium, which go back to Fukushima and Weibel and a couple of others, plus the faster computers, the graphics cards, and when Dan and Uli Meyer, the other one of this team, when they worked on this, back then there was no convenient software package. There was no TensorFlow. There was no PyTorch that does everything for you. No, one really had to know exactly what are these GPUs doing and what is the L2 cache doing and how can you use the properties of the L2 cache to make everything fast. And that's how it was possible to make these CNNs 60 times faster than equivalent code on CPU. And so suddenly we could train within 1 week a deep network like that on a training set, which would have taken 1 year or something like that on CPU.
Thank you again. Now, again, if I look at the questions by students, and maybe this is my own curiosity also, is actually pertains to general intelligence. And you have, of course, touched upon this through your discussion on meta-learning. So the question is, will general purpose intelligence be possible? And me being a natural language processing researcher, dream of a general purpose natural language processor, a machine that does sentiment analysis, also does machine translation, also does question answering, just like human beings do. We are, I think, general purpose natural language processors. So what would be your thoughts on this?
Yeah, I think language is such a universal thing that to become a really good language processor, you probably want to be a robot that is really connected to the physical world. And when you are talking about the cat that fell from the tree, yes, you can train systems to answer questions like, did the cat fall from the tree, by just analyzing huge amounts of text data. You can do that. But what do humans do? How do they know what it means that a cat fell from the tree? Well, because they also have eyes, and they see the physical world, and there's the tree, and there's the cat falling down from the tree, and this is a video which is coming in, and there are noises coming in, and the cat is making noises as it is falling from the tree, and the human being already has a lot of experience about cats and trees, because it interacted for many years before this event with the world, such that it knew that that the human knows all kinds of things about trees and cats and so on. And so now somebody says, as the cat is falling from the tree, and the cat is falling from the tree, and suddenly there's a way of correlating the video and the noises which are coming in with the text. And if you have a lot of training material of that type, then you can also understand what all these sentences mean in the real world. What do they really mean? What are the physical sensory experiences that are connected to these sentences? And it seems to me that a truly intelligent device is going to have a huge advantage if it not only sees the letters and the words and the sentences, but also sees the real world and can actually actively manipulate and influence the real world through its manipulators, through its hands, and it can stroke the cat through an active movement of the hand, and it can maybe save the cat by capturing it as it is falling down from the tree, and all these things. So a system that has experience with all the physical world, in addition to the written text, will have a huge advantage. So I think true intelligence will come through interactions with the physical world, in addition to all the knowledge that you can gain from texts. And it is already today possible to build systems that do have access to all these different sources of information, and even to build systems that actively use this knowledge to plan ahead sequences of actions that are hopefully good for them, as opposed to sequences of actions that they want to avoid because they lead to predicted failure or low predicted reward, and so on. So the general purpose AI is going to be achieved through reinforcement learning systems that maximize pleasure and minimize pain, but also have a predictive model of the world, which is being trained from all the sensory inputs that are coming in, not only from the language data and not only from the written text, but also from all the this wealth of information that you can gain from the physical world.
Yeah, thank you. So again, you touched upon a number of very fundamental points. General intelligence will require general knowledge base. It will require multimodality. It will require active agent interacting with the environment. I recall doing a course called Society of Mind, which Professor Marvin Minsky used to teach in MIT. And I remember the days of AI, which were led by Marvin Minsky, McCarthy, Roger Schank. So, what is your thought on that kind of AI, which really doesn't make use of much of learning or much of probability and statistics?
Yeah, well, so much of the AI since the 1954s, so since 1954, from the Dartmouth Conference, actually is not very modern in the sense that it doesn't have much to do with neural networks. No, it's about logic programming and expert systems and so on. And so it actually goes back to what Gödel started in 1931. So Gödel was the guy who founded theoretical computer science, basically, by showing what is the limit of computation, what are the limits of artificial intelligence. He showed there are certain formal statements that no AI can prove because they are not provable through a computational theorem prover. So no computational device, such as an AI, can break these fundamental limits of computation. That's what Gödel showed, and later people like Church and Turing, they elaborated on that. And so this whole business of theorem proving and deduction, that was dominant then in the 50s and 60s and 70s in some fields of AI. But long before this type of AI, there was a different type of AI. It wasn't called AI, it was called cybernetics. But this old cybernetics is really about devices that interact with the world, and they have neural networks and stuff like that. And that is much older, and it's much more modern, because modern AI is about deep learning neural networks, which is much more like this old AI, cybernetics, than what happened in between. And for example, Marvin Minsky, he became well known by writing a book in 1969 about the limits of perceptrons, which is the simplest type of neural network, one layer neural networks, basically. And he did that 4 years after the problem was solved. And maybe Minsky didn't know that the problem was solved. The problem was solved in 1965 in the Soviet Union, of all places, by Ivagnenko and Lapa. They had the first deep learning networks, so variants of cybernetic devices, if you will, and they had the first deep networks that really learned, and they were able to learn all kinds of things that were addressed later in Marvin Minsky's book, which was 4 years too late. So maybe Minsky didn't know that the problem already was solved in the Soviet Union, but he should have known. He should have known. And so this intermezzo of logic-based AI and deductionist AI and expert systems, and so that lasted roughly until the 80s, but then it was surpassed, or it was pushed away by certain types of machine learning that were not neural networks, like support vector machines, by another Russian guy, by Vapnik and his pupils, who really built lots of careers on that. And then in the 2000s, the artificial neural networks came up. So again, AI history has to be rewritten. It's not the stuff that started in 1954 in Dartmouth. No, it's the stuff that started much earlier in terms of cybernetics. And the first pioneer, actually, of AI of the 20th century, as far as I can tell, was the Spaniard, the Spanish guy, Quevedo, who already in 1914, so more than 100 years ago, had the first working chess endgame player. He had a chess endgame player more than 100 years ago, a device for doing that. And back then, chess was considered an intelligent activity, and somebody who could solve the problem, or to a certain extent solve the problem of endgame chess, was a total pioneer. And even in 1950, when there was this other conference on AI in Paris, where Norbert Wiener, a famous cybernetics guy, played against this old device, was still considered very impressive. So you see that back then it took many decades to improve the state of the art and something that was built in 1914 still was considered very impressive in 1950, while today, every few years, there's another even more impressive thing, because now computational power is now really helping a lot to improve things more quickly.
Thanks a lot. I think we are out of time, but a very quick question at the end, maybe. For getting a good training to become a good AI researcher, physics, mathematics, of course, are important. What would be the role of humanities and social sciences subjects?
So if you want to build AIs, it probably doesn't help a lot to study social sciences. On the other hand, the social sciences are important for lots of other things, and the reason for that is because people are social beings and they interact with each other all the time. And today they have new ways of interacting with each other through smartphones and whatever, mobile communication. And on the other hand, the whole field of the social sciences is experiencing an upturn in terms of quantitative analysis, because many people are getting data, or many scientists are collecting data from all these mobile devices in a way that wasn't possible before, and they learn to predict what big masses of humans are probably going to do, and they learn to analyze masses of humans in ways that were not possible before. So maybe it's the case that AI and predictions through neural networks are helping the social sciences to become more quantitative types of sciences. On the other hand, the social sciences themselves don't help AI, the progress of AI so much, except that the social sciences are providing lots of interesting problems to which AI can be applied.
Thank you very much. And I wish the conversation continued with this great insight that we are obtaining in the field. But we are out of time. Ashay, what is the next step now? We can conclude. Okay. So thanks a lot, Professor Schmidhuber. Thanks for your presence and very, very insightful conversation. I'm sure students, teachers, researchers have benefited a lot from this interaction, even if short. And there is a saying in India that even one moment of association with a wise man is worth 1,000 hours of association with thousands of other people. So we've got that association, and thank you very much once again.
Now, obviously, it is me who got this association by speaking to you, and I hope that the audience out there has enjoyed our little discussion, and I thank you so much for your attention, and I hope you will have a very pleasant rest of this conference.
Thank you. Thank you very much.